Welcome back. I'm here with an answer to academicians and historic philosophers' questions. Where did we come from? And why is the universe why it is, or the way it is? Through one of the world, ever research is made that reveal real and factual evidences of philosophy, science, space and time. This is the Stephen Hawkins, A Brief History of Time, a book that more than 10 million copies are sold over the world countries, which are 2 million sellers second Z. As I can directly quoted from Hawkins himself, he said, "I did not write a poet to the original edition of A Brief History of Time that was done by Carl Sagan. Instead, I wrote a short piece titled Acknowledgement, in which I was advised to thank everyone. Some of the foundations that had given me support weren't pleased to have been mentioned. However, because it led to a great increase in applications. I don't think anyone, my publishers, my agent or myself, expected the book to do anything like as well as it did. It was the London Sunday Times bestseller list for 237 weeks, longer than any book. Apparently, the Bible and Shakespeare aren't counted. It has been translated into something like 40 or 50 languages and has sold about one copy for every 750 men, women, and world. As Nathan Midbold of Microsoft, as a former postdoc of mine, remarked, I have sold more books on physics than Madonna has said or sell on sex. The success of A Brief History indicates that there is widespread interest in the big questions like where did we come from and why is the universe the way it is. I have taken the opportunity to update the book and include new theoretical and observational results obtained since the book was first published. On April Fool's Day 1988, I have included a new chapter on wormholes and time travel. Einstein's general wormholes or theory of relativity seems to offer the possibility that we could create and maintain wormholes, little tubes that connect different regions of space-time. If so, we might be able to use them for rapid travel around the galaxy or travel in time. And of course, we have not seen anyone from the future. Or have we? But I discuss a possible explanation for this. I also describe the progress that has been made recently in finding dualities or correspondences between apparently different theories of physics. These correspondences are a strong indication that there is a complete unified theory of physics, but they also suggest that it may not be possible to express this theory in a single fundamental formulation. Instead, we may have to use different reflections of the underlying theory of different solutions. It might be like our being unable to represent the surface of the earth on a single map and having to use different maps in different regions. This will be a revolution in our view of the unification of the laws of science, but it will not change the most important point, that the universe is governed by a set of rational laws that we can discover and understand. On the observational side, by far the most important development has been the measurement of fluctuations in the cosmic microwave background radiation by COBE, that is, the Cosmic Background Explorer Satellite, and other collaborations. These fluctuations are the fingerprints of creation, tiny initial irregularities in the otherwise smooth and uniform early universe that later grew into galaxies, stars, and all the structures we see around us. Their form agrees with the predictions of the proposal that the universe has no boundaries or edges in the imaginary time direction. But further observations will be necessary to distinguish this proposal from other possible explanations for the fluctuations in the background. However, within a few years, we should know whether we can believe that we live in a universe that is completely self-contained and without beginning or end. Thank you. I'm Stephen Hawkins. Note, these are digital and audio-visual documentaries meant for reserving and learning the academic researches made by the world's incomparable geniuses with high gradable IQs that can't be calculated. Now, I'm heading directly to the documentation of chapter 1, thus our picture of the universe. A well-known scientist, some say it was Bertrand Russell, once gave a public lecture on astronomy. He described how the Earth orbits around the Sun and how the Sun, in turn, orbits around the center of a vast collection of stars called our galaxy. At the end of the lecture, a little old lady at the back of the room got up and said, "What you have told us is rubbish. The world is really a flat plate supported on the back of a giant tortoise." The scientist gave a superior smile before replying, "What is the tortoise standing on?" "You are very clever, young man, very clever," said the old lady. "But it is turtles all the way down." Most people will find the picture of our universe as an infinite tour of tortoises rather ridiculous. But why do we think we know better? What do we know about the universe? And how do we know it? Where did the universe come from? And where is it going? Did the universe have a beginning? And if so, what happened before then? What is the nature of time? Will it ever come to an end? Can we go back in time? Recent breakthrough in physics, made possible in part by fantastic new technologies, suggest answers to some of these long-standing questions. Someday, these answers may seem as obvious to us as the Earth orbiting the Sun, or perhaps as ridiculous as a tour of tortoises. Only time, whatever that time may be, will tell. As long ago as 340 BC, the Greek philosopher Aristotle, in his book On the Heavens, was able to put forward two good arguments for believing that the Earth was a round sphere that rather than a hard plate. First, he realized that eclipses of the moon were caused by the Earth coming between the Sun and the moon. The Earth's shadow on the moon was always round, which will be true. The shadow would be truly only if the Earth was spherical. Also, the shadow will have been elongated and elliptical unless the eclipse always occurred at a time when the Sun was directly under the center of the disk. Secondly, the Greeks knew from their travels that the North Star appeared lower in the sky when viewed in the south than it did in more northerly regions. Since the North Star lies over the North Pole, it appears to be directly above an observer at the North Pole. But to some looking from the equator, it appears to lie just as the horizon. From the difference in the apparent positions of the North Star in Egypt and Greece, Aristotle even quoted an estimate that the distance around the Earth was 400,000 stadia. It is not known exactly what length a stadium was, but it may have been about 200 yards, which will make Aristotle's estimate about twice the currently accepted figure. The Greeks even had a third argument that the Earth must be round, for why else does one first see the sails of the ship coming over the horizon and only later see the whole. Aristotle told the earth was stationary and that the sun, the moon, the planets, and the stars moved in circular orbits about the earth. He believed this because he felt, for mystical reasons, that the earth was the center of the universe and that circular motion was the most perfect. This idea was elaborated by Ptolemy in the 2nd century AD into a complete cosmological model. The earth stood at the center, surrounded by 8 spheres that carried the moon, the sun, the stars, and the 5 planets known at the time as Mercury, Venus, Mars, Jupiter, and Saturn. The planets themselves moved on smaller cycles attached to their respective spheres in order to account for their rather complicated observed parts in the sky. The outermost sphere carried the so-called fixed stars, which always stay in the same positions relative to each other, but which rotate together across the sky. What lay beyond the last sphere was never made very clear, but it certainly was not part of mankind's observable universe. Ptolemy's model provided a reasonably accurate system for predicting the positions of heavenly bodies in the sky. But in order to predict these positions correctly, Ptolemy had to make an assumption that the moon followed a path that sometimes brought it twice as close to the earth as at other times. And that meant the moon ought sometimes to appear twice as big as other times. Ptolemy recognized this flaw, but nevertheless, his model was generally, although not universally, accepted. It was adopted by the Christian Church as a picture of the universe that was in accordance with the scripture, for it had the great advantage that it left loads of room outside the sphere of fixed stars for heaven and hell. A simpler model, however, was proposed in 1514 by a Polish priest, Nicholas Copernicus. At first, perhaps for fear of being branded a heretic by his church, Copernicus circulated his model anonymously. His idea was that the sun was stationary at the center and that the earth and the planets moved in circular orbits around the sun. Nearly a century passed before this idea was taken seriously. Then 2 astronomers, the German Johannes Kepler and the Italian Galileo Galilei, started publicly to support the Copernican theory, despite the fact that the orbits as predicted did not quite match the ones observed. The death blow to the Aristotelian and Ptolemaic theory came in 1609. In that year, Galileo started observing the night sky with a telescope, which had just been invented. When he looked at the planet Jupiter, Galileo found out that it was accompanied by several small satellites or moons that orbited around it. This implied that everything did not have to orbit directly around the earth. But as Aristotle and Ptolemy had thought, it was of course still possible to believe that the earth was stationary at the center of the universe, and that the moons of Jupiter moved on extremely complicated paths around the earth, given the appearance that they orbited Jupiter. However, Copernicus' theory was much simpler, and at the same time, Johannes Kepler had modified Copernicus' theory, suggesting that the planets moved not in cycles, but in ellipses, and an ellipse is an elongated cycle. The predictions now finally matched the observations. Don't forget, all what Stephen Hawkins is trying to say here at this introduction is, where did the earth come from? Why is the earth the way it is? And will the earth end Does it have a beginning? How does the earth start? Let us continue. As far as Kepler was concerned, elliptical orbits were merely an ad hoc hypothesis, and a rather repugnant one at that, because ellipses were clearly less perfect than cycles. Having discovered almost by accident that elliptical orbits fit the observations well, he could not reconcile them with his idea that the planets were made to orbit the sun by magnetic forces. An explanation was provided only much later in 1687, when Sir Isaac Newton published his Philosophiae Naturalis Principia Mathematica, probably the most important single work ever published in the physical sciences. In it, Newton not only put forward a theory of how bodies move in space and time, but he also developed the complicated mathematics needed to analyze those motions. In addition, Newton postulated a law of universal gravitation, according to which each body in the universe was attracted toward every other body by a force that was stronger the more massive the bodies and the closer they were to each other. It was this same force that caused objects to fall to the ground. The story that Newton was inspired by an apple hitting his head is almost certainly apocryphal. All Newton himself ever said was that the idea of gravity came to him as he sat in a contemplative mood and was occasioned by the fall of an apple. Newton went on to show that, according to his law, gravity causes the moon to move in an elliptical orbit around the earth and cause the earth and the planets to follow elliptical paths around the sun. The Copernican model got rid of Ptolemy's celestial space, and with them, the idea that the universe had a natural boundary. Since fixed stars did not appear to change their positions apart from a rotation across the sky caused by the earth spinning on its axis, it became natural to suppose that the fixed stars were objects like our sun, but very much further away. Newton later realized that, according to his theory of gravity, the stars were other, so it seemed they could not remain essentially motionless. Would they not all fall together at some point? In a letter in 1691 to Richard Bentley, another leading thinker of his day, Newton argued that this will indeed happen if there were only a finite number of stars distributed over a finite region of space. But he reasoned that if, on the other hand, there were an infinite number of stars distributed more or less uniformly over infinite space, this will not happen because there will not be any central point for them to fall to. This argument is an instance of the pitfalls that you can encounter in talking about infinity. In an infinite universe, every point can be regarded as the center because every point has an infinite number of stars on each side of it. The correct approach, it was realized only much later, is to consider the finite situation in which the stars all fall in on each other, and then to ask how things change if one adds more stars roughly uniformly distributed outside this region. But according to Newton's law, the extra stars will make no difference at all to the original ones on average. So the stars will fall in just as fast. We can add as many stars as we like, but they will still always collapse in on themselves. We now know it is impossible to have an infinite static model of the universe in which gravity is always attractive. Even those who realized that Newton's theory of gravity showed that the universe could not be static did not think to suggest that it might be expanded. Instead, they attempted to modify the theory of making the gravitational force repulsive at very large distances. This did not significantly affect their predictions of the motions of the planets, but it allowed an infinite distribution of stars to remain in equilibrium, with the attractive forces between nearby stars balanced by the repulsive forces from those that were farther away. However, we now believe such an equilibrium will be unstable. If the stars in some region got only slightly nearer each other, the attractive forces between them will become stronger and dominate over the repulsive forces, so that the stars will continue to fall toward each other. On the other hand, if the stars get a bit further away from each other, the repulsive forces will dominate and drive them further apart. Another objection to an infinite static universe is normally ascribed to the German philosopher Heinrich Olbers, who wrote about this theory in 1823 AD. In fact, various contemporaries of Newton's had raised the problem, and the Olbers article was not even the first to contain plausible arguments against it. It was, however, the first to be widely noted. The difficulty is that in an infinite static universe, nearly every line of sight will end on the surface of a star. Thus, one will expect that the whole sky will be as bright as the sun, even at night. Olbers' counter-argument was that the light from distant stars will be dimmed by absorption by intervening matter. However, if that happened, by intervening matter will eventually heat up until it glowed as brightly as the stars. The only way of avoiding the conclusion that the whole of the night sky should be as bright as the surface of the sun would be to assume the stars had not been shining forever, but had turned on at some finite time in the past. In that case, the absorbing matter might not have heated up yet, or the light from distant stars might not yet have reached us. And that brings us to the question of what could have caused the stars to have turned on in the first place. Now, the beginning of the universe had, of course, been discussed long before this. According to a number of early cosmologies and the Jewish, Christian, Muslim traditions, the universe started at a finite and not very distant time in the past. One argument for such a beginning was the feeling that it was necessary to have first cause to explain the existence of the universe. Within the universe, you always explained one event as being caused by some earlier event. But the existence of the universe itself could be explained in this way only if it had some beginning. Another argument was put forward by St. Augustine in his book, The City of God. He pointed out that civilization is progressing and we remember who performed this deed or developed that technique. Thus men, and so also perhaps the universe, could not have been around all that long. St. Augustine accepted a date of about 5000 BC for the creation of the universe according to the book of Genesis. It's interesting that this is not so far from the end of the last ice age, about 10,000 BC, which is when archaeologists tell us that civilization really began. The questions of whether the universe had a beginning in time and whether it is limited in space were later extensively examined by the philosopher Immanuel Kant in his monumental and very obscure work, Critique of Pure Reason, published in 1781. He called these questions antinomies, that is, contradictions of pure reason, because he felt that there were equally compelling arguments for believing the thesis that the universe had a beginning and the antithesis that it had existed forever. His argument for the thesis was that if the universe did not have a beginning, there will be an infinite period of time before any event, which he considered absurd. And I considered it same. The argument for the antithesis was that if the universe had a beginning, there will be an infinite period of time before it. So why should the universe begin at any one particular time? In fact, his cases for both the thesis and the antithesis are really the same argument. They are both based on his unspoken assumptions that time continues back forever, whether or not the universe had existed forever. As we shall see now, the concept of time has no meaning before the beginning of the universe. This was first pointed out by St. Augustine when asked, "What did God do before he created the universe?" Augustine didn't reply. He was preparing hell for people who ask such questions. Instead, he said that time was a property of the universe that God created, and that time did not exist before the beginning of the universe. Actually, it was because St. Augustine had no answer to give. In order to talk about the nature of the universe and to discuss questions such as whether it has a beginning or an end, you have to be clear about what a scientific theory is. I shall take the simple-minded view that a theory is just a model of the universe or a restricted part of it, and a set of rules that relate quantities in the model of observations that we make. It exists only in our minds and does not have any other reality, whatever that may mean. A theory is a good theory if it satisfies two requirements. It must accurately describe a large class of observations on the basis of a model that contains only a few arbitrary elements, and it must make definite predictions about the results of future observations. For example, Aristotle believed Empedocles' theory that everything was made out of four elements: earth, air, fire, and water. This was simple enough, but did not make any definite predictions. On the other hand, Newton's theory of gravity was based on an even simpler model, in which bodies attracted each other with a force that was proportional to a quantity called their mass and inversely proportional to the square of the distance between them. Yet, it predicts the motions of the sun, the moon, and the planets to a high degree of accuracy. Any physical theory is always provisional, in the sense that it is only a hypothesis. You can never prove it, no matter how many times the results of experiments agree with the sum theory. You can never be sure that the next time the result will not contradict the theory. And on the other hand, you can disprove a theory by finding even a single observation that disagrees with the predictions of that particular theory. As philosopher of science Karl Popper has emphasized, a good theory is characterized by the fact that it makes a number of predictions that could in principle be disproved or falsified by observation. Each time new experiments are observed to agree with the predictions, the theory survives and our confidence in it is increased. But if ever a new observation is found to disagree, we have to abandon or modify the theory. At least, that is what is supposed to happen. But you can always question the competence of the person who carried out the observation. Today, scientists describe the universe in terms of two basic partial theories: the general theory of relativity and quantum mechanics. They are the great intellectual achievements of the first half of this century. The general theory of relativity describes the force of gravity and the large-scale structure of the universe. That is, the structure on scales from only a few miles to as large as a million million. That's one with 24 zeros after 8 miles. The size of the observable universe. Quantum mechanics, on the other hand, deals with phenomena on extremely small scales, such as a millionth of an inch. Unfortunately, however, these two theories are known to be inconsistent with each other. They cannot both be correct. One of the major endeavors in physics today, and the major theme of this book, is a search for a new theory that will incorporate them both. A quantum theory of gravity. We do not yet have such a theory, and we may still be a long way from having one. But we do already know many of the properties that it must have, and we shall see in later chapters that we already know a fair amount about the predications of quantum theory of gravity must make. Now, if you believe that the universe is not arbitrary but is governed by definite laws, you ultimately have to combine the partial theories into a complete unified theory that will describe everything in the universe. But there is a fundamental paradox in the search for such a complete unified theory. The ideas about scientific theories outlined above assume we are rational beings who are free to observe the universe as we want and to draw logical deductions from what we see. Because the partial theories that we already have are sufficient to make accurate predictions in all but the most extreme situations, the search for the ultimate theory of the universe seems difficult to justify on practical grounds. It is worth nothing, though, that similar arguments could have been used against both relativity and quantum mechanics, and these theories have given us both nuclear energy and the microelectronics revolution, the discovery of a complete unified theory, therefore may not aid the survival of all species. It may not even affect our lifestyle, but ever since the dawn of civilization, people have not been content to see events as unconnected and inexplicable. They have craved an understanding of the underlying order in the world. Today, we still yearn to know why we are here and where we came from. Humanity's deepest desire for knowledge is justification enough for our continuing quest, and our goal is nothing less than a complete description of the universe we live in. Thank you. We meet in the continuation of episode 2 of the Hawkins History of Time. That's the beginning, the space and time. That's where the history of the universe begins. Now it's an argument of the foreword, of the introduction, of the acknowledgements that we all go through. The arguments that scientists have of about 10,000 years BC and AD. Thank you, and don't forget